I'd like to welcome everyone to the second day of the International Space Medicine Summit. I think this is a very special day. The first panel will be on new frontiers in space medicine. This is a panel that's put in place to pretty much be a placeholder for what's current and what are the current needs for spaceflight in regard to science and these sort of things. And Mike Barratt has been, and Serena have both been very critical in putting together these panels. And they're in the middle of operations and science and flight, and are just perfect to do that. And Mike has been doing this for many years. Mike is from Washington State. He went to University of Washington for his undergraduate degree, and then medical school at Northwestern University, and residency in internal medicine at Northwestern. Then later went to Wright State University and got an aerospace medicine residency as well. He went to NASA and became a NASA flight surgeon. Was very instrumental in opening up medical support for NASA at the Gagarin Cosmonaut Training Center, and then later became an astronaut. And he flew on Expedition 19 and 20 to the International Space Station for a long duration flight, and then flew on STS-133. On the science side, for 2 years, he was the Human Research Program Manager at JSC, and has had a tremendous amount of experience in analog environments like caves and NEMO and these sort of things. He knows what's going on in operations. He knows what's going on in the science area. He's a flown astronaut, and he's perfect for this panel. And I think he's put together an outstanding panel to look at current events. So I'll turn it over to Mike.
Okay, thanks very much, Richard. I will say there's a couple of our speakers who are knocking at the virtual door, and hopefully will be into us very soon. But I think we've got the bulk of us, and we're really happy to get started. You know, like Richard said, we use the New Frontiers panels to give us an opportunity to bring topics to this community, which I think is a fairly diverse human spaceflight community. And these are emerging topics that are very relevant. They're relevant in either scientific findings that a lot of us may otherwise not encounter without a deliberate search. And along with these investigational findings, there's new operational and systems development efforts going on. And these serve to prepare and equip astronauts for next generation spaceflight missions. So today we're extracting from both of these broad areas. We'll touch on neuroanatomical and neurobehavioral research, cell biology findings, two very exciting analog venues, and new generation EVA suits, extravehicular activity suits, and spacecraft habitats. We're going to start with everyone's favorite organ, the brain. There have been several publications in recent years, for those of you that follow space medical literature, and these have been demonstrating both structural and functional changes in the central nervous system associated with spaceflight. A lot of us are familiar with the spaceflight associated neuroocular syndrome, but that's probably the tip of the iceberg. There's probably much more global changes, and I think these are unfolding as these new studies come out. Now, often these studies are accompanied by rather sensationalistic press and popular press reports and speculations, and sometimes emails from my mother asking if this explains anything about my own behavior. But clearly there's a prerogative here to understand these changes and what they're telling us, particularly as we expand the population base of flyers. We're going to see an explosion and a very large diversity of people who are going to be flying in space. And this is something we need to know. So we're very fortunate to have two lead authors from two of these recently published investigations. And we're going to start with Dr. Stephen Jillings. It's a great pleasure to me to really introduce some of our young rising rock star researchers in the space medicine world. And Dr. Jillings is just that. He studied biomedical sciences at the University of Antwerp in Belgium, and then followed the neuroscience program during his master's degree. He recently completed a joint PhD program between the University of Antwerp for space science and the University of Liège in Belgium in medical sciences. And the title of his doctoral thesis was something very germane to us: the effect of long-duration spaceflight on brain structure and function. Why he chose that, hopefully he'll give us a couple of words on, but a very niche field, but expanding rapidly. Currently, he's continuing this project as a postdoc researcher at the University of Antwerp. And it was his seminal paper, which was entitled Macro and Microstructural Changes in Cosmonauts' Brains After Long Duration Spaceflight, that really caught my attention. This was published in Science Advances last year. It was quite good. It drew very deserved attention and has already been cited fairly widely. So with that, I will give the floor to Dr. Jillings.
All right, great. Hello, everyone, and thank you, Mike, for the very nice introduction. Thanks for the organizers for also inviting me here to talk about this, for everyone, interesting topic. So the background of my talk starts with the fact that we didn't know for a long time what was actually happening to the brain as a result of space missions. It was evident from a functional and behavioral perspective that astronauts were able to adapt to the microgravity environment and also readapt when back on Earth. And so logically, it must be the case that the brains of astronauts undergo neuroplasticity, which is the brain's ability to adapt to new circumstances. So our research group actually started the first prospective MRI study where Russian cosmonauts were scanned before their space mission, shortly after, and again 7 months afterwards as a follow-up measurement. And this allows us to study brain structural and functional changes due to spaceflight with the aim of eventually mapping out those regions that show signs of neuroplasticity. So in 2016, the first results on brain changes due to spaceflight using MRI were published by our group. And this is actually pretty striking that human spaceflight has been going on for 60 years. And only 5 years ago, we actually got first insights into these MRI-based brain changes. So currently, there are several research projects conducted by our group and our American colleagues to study the effects of spaceflight on the brain. And some of the first results that came from a few of these studies actually found many effects that were not directly attributable to neuroplasticity, nor were they actually anticipated. So in short, what we and others found was that the brain was uplifted within the skull, and we see that the fluid, the CSF around the brain actually redistributes. The brain ventricles, also containing the CSF, expand, and we see a kind of a complex change in gray matter structure. All these findings were pretty much explained within the framework of the upward fluid shift phenomenon that occurs in microgravity. So specifically, the upward shift of bodily fluids in microgravity affects this balanced circulation of CSF, and that's why we see these redistributions of the fluid and also gray matter structural changes. So the title of this talk was indeed Macro and Microstructural Changes in Cosmonauts' Brains, which is the title of the publication that Dr. Barratt referred to. And it deals with the diffusion MRI data collected in cosmonauts. And so a brief technical part to explain the rest of my talk is that, so you should imagine that an MRI scan consists of voxels in a similar way that pictures consist of pixels. And in each of these voxels, we get a value that reflects some kind of biological tissue property, for example, fluid or fat or brain tissue. And but the diffusion MRI technique that we used actually goes a little beyond that. And we can infer from this technique that a voxel contains, for example, 60% gray matter, 40% CSF or free water. So you can think about these values as a sort of density, where you have a certain amount of brain tissue or a certain amount of fluid within a volume unit. And interestingly, we can also look at volume changes with MRI data. And if we then combine this density with volume changes, we can actually also infer whether there are changes in mass or the net amount of the fluid or the brain tissue. And this just follows the basic physical relationship between density, mass, and volume. And although these metrics from MRI are strictly spoken not exactly mass and density, the relationship is very analogous, and they can be very well interpreted as such. So I will also use these terms throughout the rest of this talk. Okay, so the way that this diffusion MRI technique applies to cosmonaut MRI data will be now explained through several of the main results of this paper. And so the first result is that we see that both the density and the mass of CSF change throughout the whole brain. And this reflects the fact that the CSF is indeed redistributing along the brain, where we see less CSF at the top part of the brain and more at the bottom. And this corresponds fully with what we saw with previous analyses as well, and also reflects again this upward shift of the brain within the skull. So it actually pushes aside the CSF around it, and it then accumulates back at the bottom of the brain. A second result is that we also saw large spread changes in gray matter density, but this time there was no change in the net amount or the mass of the gray matter. So what we concluded from this finding is that the effect of spaceflight on the gray matter is actually purely this remodeling effect without it changing the net amount of the gray matter. So to give an example, we talked about the top of the brain that shifts up. So the CSF disappears there or decreases in this region. And this actually causes the cortical gyri, so the brain's gyri, to become more compact and kind of squeeze together a bit more. And this is what we actually detect in the form of this density increase, because there is more of the gray matter in this volume. So, and then a third result is that we did not see any decreases in the amount of gray matter or white matter throughout the brain. So it's important to notice that this technique that we used would have been able to detect regions in the brain where there's, like say, tissue loss, but we did not find such changes, which is a reassuring finding. Now, besides these observations about remodeling effects and fluid shift effects, we also saw some local regions where the net amount of gray matter or white matter increased. And we saw such results in the basal ganglia, the primary motor cortex, and the cerebellum. And all these three regions are involved in motor strategies and motor learning. And we know that astronauts pose alterations in these systems, or they need to adapt and change their motor strategies and relearn their movement strategies. So because the net amount of the brain tissue increased, these findings can't really be explained by the remodeling effects that we see throughout most other parts of the brain in the gray matter. So the most likely explanation for these findings remain neuroplasticity. Now, there are several knowledge gaps still that we want to address in the future. So first of all, we don't have any data yet on the influence of mission duration and previous space experience on these brain changes. So bearing in mind that future missions to space will last significantly longer than 6 months, and that accessibility to space will increase even more, these are important questions to address. And we need to collect more data to be able to perform such analyses. So specifically, we need to characterize a dose response curve for the changes occurring in the brain in function of mission duration. And we also need to assess whether the effects occurring in the brain accumulate throughout repeated missions to space. A second thing is that there are numerous hypotheses now that put forward that the observations from MRI data are related to the spaceflight-associated neuroocular syndrome, or SANS. So both SANS and the MRI findings are believed to be the result of this upward fluid shift caused by microgravity. And this suggests that there is a common mechanism at hand. Yet this has not been demonstrated yet, and there's no prospective study to properly investigate this yet. And similarly, it has yet to be determined whether the observed brain changes pose any negative consequences to astronaut performance and health, which would direct us to developing necessary countermeasures. But however, the fact is that astronauts now go to multiple times to space, and generally they are in a good physical and mental state after a few weeks of adaptation back on Earth. So this bears no immediate concern at this stage in comparison, for example, SANS. But nevertheless, it is again worth stressing that this line of research must continue when we know that humans will travel longer and further into space. So to summarize what we learned so far, the brain undergoes this complex three-dimensional shifts together with this fluid redistribution. And most of these findings were not anticipated among many of the involved researchers and often pose some difficulties in interpretation. But so this diffusion MRI work I described was actually the first technique to apply to space crew that was able to figure out more about the nature of the brain in more detail, about the changes to the brain in more detail. So it allows us to show regions where neuroplasticity occurs, and it demonstrated that the gray matter changes are mostly remodeling effects and that no net loss of brain tissue was evident. So we are eager to continue this very fascinating quest, and I'm looking forward to your questions. Thank you.
All right, brilliant. And just for the audience listening, we would like to go through all of the panel and then open it up for questions, just to be sure that everybody gets a chance to message. With one exception I do have for Dr. Jillings, and that, first of all, I think this is fascinating. I'm glad to know that I probably didn't lose brain tissue, but maybe just redistributed it. But you mentioned a dose response curve and worrying about longer duration missions. My question might be highly speculative, but what about shorter duration missions? As we open this up, we're going to be seeing most commercial space flyers, space tourists, spaceflight participants flying fairly short missions. And so the question is, how quickly might you see this? Would you see it, say, within a few days of low Earth orbit? I realize we haven't done that yet, but is that a target of your intended study?
Yeah, so that's indeed a very good question. So actually, the American colleagues that perform similar research than we do, they have often included the shuttle astronauts as a group to which they compared the ISS astronauts to. And it is pretty clear that all the changes that we see about these fluid redistributions and so on are actually pretty typical for longer duration missions. So 6 months, when it exactly starts, we don't know, probably gradually builds up, but most of the 14-day average flights of the shuttle do not seem to actually change the brain in the way that we see it with the ISS missions.
Okay, very good. Then I would like to go then directly to our next speaker, and I think it's a wonderful comparison, contrast, if you will, but from a young researcher to what I would consider an elder statesman in the world of neurobehavioral and neuroplasticity research. Dr. Ajitkumar Mulavara comes to us with a background in neuroscience and biomedical engineering. He is the portfolio scientist for the Central Nervous System Behavioral Medicine and Sensory Motor Project, which we call the CBS project, at the NASA Human Research Program here at the NASA Johnson Space Center. As part of the portfolio transdisciplinary leadership team, he works to help characterize and mitigate the risks associated with potential synergistic interaction with the central nervous system, resulting from simultaneous exposure to multiple compounded spaceflight hazards, which I think a lot of you are aware of. These include the confinement, spaceflight radiation, isolation, altered gravity, carbon dioxide, other toxic constituents. So it's not an easy field to try and untangle the effects of zero gravity and all of these other compounded factors. Dr. Mulavara, for those who follow this literature, is a very prolific investigator and author in the area of spaceflight-induced alterations in neurosensory function, and in particular the effects of on post-flight performance and recovery. This as you might guess, is very much at the forefront of our planning for exploration class missions, and of course the build of new vehicles right now. So I've asked Dr. Mulavara to come and give us a bit of a holistic overview of brain effects and neuroplasticity associated with spaceflight. So Ajit, I give the floor to you.
Thank you, Mike. So good morning, friends. I hope you can hear me and see my video. Cool. So good morning, friends. Ladies and gentlemen, I want to thank Mike for this excellent opportunity to join the panel, and to Mr. Abbey and other organizers of the ISMS Summit for providing a forum to present the synopsis on a holistic crew review of brain changes and neuroplasticity. Now, one disclaimer here at the outset, I'll say to my colleagues, it's difficult to cover all the shown changes in the brain and examples of neuroplasticity. And if interested, I'm happy to share a review paper that was published recently. I can post the citation in the chat after my talk. To tee off from where Dr. Jillings left, by the way, excellent talk there, and then the follow-up question that Mike had off of him, I'll try to elucidate some of the findings from various groups that answer some of those questions directly that Dr. Jillings raised at the end, associated with pre-flight experience, as well as with how long the changes last, associated with the duration of missions, and so on and so forth. So in general, if you follow Dr. Jillings closely, several studies reported upward shift of the brain, narrowing of the central sulcus, twisting of cerebral aqueduct, and so on and so forth, increased ventricular volumes, quantifying the cerebrospinal fluid volume shifts within the ventricles, and these changes were in the range of about 11 to 25%. Now, interestingly, recovery in the ventricular volume change is only partial. Even at, reports have tested it at 6 months, 7 months, and even at 12 months follow-up after spaceflight. Those haven't completely recovered after return. Now, follow-up analysis is showing a relationship between ventricular volume increase with the number of missions that crew members have undertaken, as well as the time between missions before their space flight. That is, more changes and more missions and less time between missions correspond to lesser change in the ventricular volume, pointing to incomplete pre-flight recovery processes. Now, current analyses of these data sets, will help elucidate the time it will take for these recovery processes to be complete, allowing normal recovery of ventricular expansion. Another aspect of the influence of cephalic fluid shifts come from analyzing free water changes in the brain. Now, free water is defined as water molecules that are in the surrounding the ventricles or extra cellular space, brain parenchyma, etc. Now, increased volume of free water is reported at the base of the brain and with decreased free water at the vertex. And the amount of free water changes in the vertex corresponds to mission duration. Shuttle being the least, followed by increased in 6 months, and with a couple of crew members tested over 1-year missions, those changes are beyond the 6-month or indicate changes beyond 6-month mission crew members. Now, analysis of variation in free water in specific areas around the right lateral ventricle shows association with the number of previous missions as well. Now, other tissues in the brain, like Dr. Jillings alluded to, include the gray matter tissue. And as he said, there are no indications of a global change in gray matter mass across the studies that have been conducted so far. Now, there are several reports of focal changes in gray matter volume in sensory motor and motor areas, but most of the changes in gray matter overlap the significant alterations that are seen in CSF and free water changes, shifting of the brain position in the skull and so on and so forth. All of these gray matter changes have been shown to have recovered in the 6-month time period at follow-up. Now, examples of changes in white matter tracts that reflect bundles of long myelinated axons have been shown as an example, superior longitudinal fasciculus. And, this particular tract is important because it's believed to play a role in visual recognition, visually guided decision-making, language comprehension, so on and so forth. Other areas that have been shown are inferior longitudinal fasciculus, inferior frontoorbital fasciculus tracts. What is important in this example is that the changes seen in the superior longitudinal fasciculus was correlated with the changes in post-flight balance control. Greater amount of disintegration resulted in greater amount of changes in balance control post-flight. Now, white matter tract changes have also been noted to be associated with motor function in tracts associated with decreases of lower limb use. Now, to elucidate examples of neuroplasticity, the functional brain organization has been studied using connectivity between brain regions and at the resting state. Now, in studies where they have followed strict bed rest analogs, these changes in connectivity have been associated with a cohort that exhibited SANS versus no SANS. And these changes in functional connectivity was shown to be associated with previously identified genetic and biochemical predictors of SANS as well. Now, other examples of neuroplasticity in cosmonauts were studied using plantar stimulation of the foot, and they have found decreased connectivity of the cerebellum to regions of proprioception, visual motor connectivity. Now, in another study that was performed on astronauts, where vestibular-specific stimulations were given, showed that crew who were able to disassociate the traditional deactivation of visual and somatosensory cortices with vestibular stimulation have a better balanced performance post-flight. Now, these brain changes recovered, all of these brain changes associated with vestibular stimulation recovered within 3 months post-flight. Now, these are all examples of what we call as sensory reweighting, matching the observed, often observed greater dependence on the visual channel post-flight in returning crew members. One of the, I wanted to conclude with an example of changes in blood biomarkers that was published recently in a cohort of 5 cosmonauts. And that was interesting because the reported blood-based biomarkers are important indicators of changes in potentially the blood-brain barrier and indicates axonal disintegration or astrocytic activation as it is shown in their paper. Now, what it does indicate is points to some of the reparatory processes post-flight in terms of flushing out the hindered waste clearance due to the cephalic shift of the brain and the subsequent restoration of the blood-brain barrier. So having said this, as many of the speakers have elucidated, the enthusiasm of long-duration spaceflight exploration, including crewed missions back to the moon and beyond, one aspect of crew members' health in achieving success in this endeavor lies in maintaining the integrity of the CNS and the brain that will be exposed to near simultaneous exposures, hazard exposures of microgravity, space radiation, and isolation. And it's important to appreciate and understand the impact and interaction of multiple stressors on the CNS. Maintaining the integrity of the CNS is very important because crew members' ability to perform many of the critical mission tasks are dependent on high-level neurovestibular, sensory, cognitive, motor processes. So with that, I'm going to close and look forward to answering questions that come up. Thank you, Mike.
All right. Thank you, Ajit. I have one quick question, which you may not be able to answer right away before we go to our next speaker, which is, do we anticipate a new round of medical operational screening procedures, which might include CNS imaging and some of these biochemical markers that might be indicative and correlate with some of the neural imaging changes that we see? So if you have a quick answer to that, great. If not, we'll catch that to the discussion. But that's part of what I hear when I think about all these new findings coming out.
Absolutely. The quick answer would be it is good if we have some of the screening tools like the blood-based biomarkers. In terms of other modalities, as you know, the time after flight is quite cramped in terms of activities that crew engage in. So that is still a TBD. But there's a lot of ongoing work, and I'm glad to discuss that in the bigger forum of chat at the end of the session.
Thanks so much, Ajit. I think this is a really exciting area. I'm going to go next to Dr. Ludmila Buravkova from the Institute of Biomedical Problems. I want to start first to explain a little bit of why I've asked Dr. Buravkova to address today's topic. And many of us in this virtual room, certainly most of us in the Johnson Space Center community, are very familiar with the systemic changes in the human body that go along with adaptation to microgravity, bone, muscle atrophy, and whatnot. But we're much less schooled on the upstream triggers, the signaling mechanisms that are triggered by gravitational unloading to stimulate these processes, which I would consider probably more macro processes, if you will. And over the last several years, there's been an increasing awareness of this interaction between individual cells and the extracellular matrix and their role in gravitational sensing, with more recent focus on the metrosome itself. Now, the metrosome may be a term new to some of you, but I like to think of it as a kind of a complete parts list a parts list of the protein constituents in any given extracellular matrix associated with a specific tissue, as well as say a larger list of the additional proteins that might be expressed in that extracellular matrix when you perturb it, when you put it under different or novel conditions, such as altered gravity loads. Dr. Buravkova and her team have really been at the cutting edge of bringing recent advances in proteomics and other methods to studying the role of the Metrosome in reduced gravity, which I think is a very exciting and very necessary area of study in our understanding of spaceflight adaptation. Dr. Buravkova may be known to many of you. She graduated from the Moscow Medical University and obtained her PhD and Doctor of Science degrees in space medicine at the Institute of Biomedical Problems. She has participated in medical support of EVA, in ground-based experiments, and of course the BION satellite programs. During 3 decades, she's contributed as a principal investigator or a co-investigator and team lead to the Space Station Mir and International Space Station Science programs. She's been a professor at Moscow State University for 20 years and mentor of the master's program in space biomedical research at the Faculty of Space Investigations. Ludmila right now is deputy director of the IBMP and head of the cell physiology lab and an active investigator. So she's massively busy, and we're very, very lucky to have her today. Those of you who know her as a passionate scientist and educator, and again, immensely busy. So I will give the floor to Dr. Buravkova.
Thank you very much, Mike. Good morning. I would like to say good morning to our American colleagues and good evening to Russian colleagues who involved in this meeting. And especially thanks to Mr. Abbey to organize this meeting. All of us remember the very nice meeting in Rice University some years ago. Now we are online, but I think we could discuss some important question. Thank you, Mike. Я перейду на русский.
So I'm going to switch into Russian, into English. I do hope
перевод будет лучше, чем мой английский.
The interpretation will be better than me speaking English. And I wanted to focus on 3 items of the discussion of our panel. I will start not with the matrix, but with dynamics. Yesterday, the discussion panel that Oleg Kontov was leading, and Julie Robertson were discussing organoids during space missions, as well as screening that is using organoids, the screening of the reaction of the physical system using organoids. I am for those experiments that allow us to study the cell level and the fabric in vitro or ex vivo. If we look at a non-simple culture such as organoids, I believe that we, Russian researchers, as well as the US researchers, need to pay more attention to genome methods. It's very easy right now to do a full genome sequencing, and we can have and study and look at the dynamic of the polymorphism of genome of a human. It doesn't mean that we must use the data for polymorphism of the candidates to cosmonauts or astronauts to impact our decision selection criteria and decision making. But we do know that cosmonauts, if those are not tourists, are special people. They specifically have been selected, specifically have been trained
работающая во время космических полетов
during
в
space
очень
missions
специфической
in
среде.
very
Я имею в
specific
виду
environment.
и
And I'm referring to
микрогравитацию, и чем
microgravity
дальше, тем больше
environment, and the more we explore
радиационную обстановку.
the space, it'll be
Поэтому
radiation
мне
impacts will be
кажется, что
affecting
крайне
more.
важно
Therefore,
знать,
I think it's
каким
extremely
образом
important to
полиморфизм генов
understand
может
how
влиять
gene
на тех или
polymorphism
иных
can
генов,
impact
тех,
different genes.
которые мы отберем и сделаем
And
лист этих
we
генов,
can
которые будем
select
проверять.
different genes and we
Каким
can
образом
check
полиморфизм генов
them. How
влияет
can
на
polymorphism
реакцию
of genes will
физиологических
affect the
систем
physical
у
reaction
космонавтов
of
и
different
каким
systems of the
образом идет
cosmonauts, as well as
адаптация?
how is the adaptation
Я
going.
понимаю, что
I
это
understand
приватные данные,
that these are
и,
private
может
data,
быть,
absolutely.
на первых
And
этапах
maybe during the
они не будут
initial stages,
доступны
they will not be accessible
всем ученым,
to
но мне
all the
кажется,
scientific
что
community.
полетным врачам
But I think the flight doctors
необходимо
will need
знать
to know
об
that
этих полиморфизмах,
about the
которые есть у
polymorphism
каждого из нас,
that all of us
и
have,
попытаться
and try
проанализировать
to analyze
различия в адаптации,
the
в
differences
том
in
числе к
adaptation,
микрогравитации, в
including
зависимости
the
от того,
microgravitational environment,
какой
depending
полиморфизм
on
генов мы
which
имеем
polymorphism of
у
genes
данного
we have
космонавта и
for this
астронавта.
particular person, cosmonaut or
Это
astronaut.
первый пункт, на
So
который
that's
мне
the
хотелось
first
бы обратить
item
внимание
that I wanted
слушателей и участников
to draw
нашей
your
панели.
attention to anybody listening and participates
Второй
in our
пункт.
discussion board.
Два
The
доклада,
second
два
item,
сообщения было
that's
о
two
мозге.
reports,
Мне хотелось бы
two
перейти к
presentations were
соединительной
about
ткани.
the brain. Now
Все
I'd like to talk about
космонавты
connection
знают,
tissue.
если я не права,
All the
то поправьте
cosmonauts know,
меня,
and if I'm wrong, then
что
please correct
не
me,
только
that
мышцы
not only
и
the
костная
muscles
система,
and the bone
которую
mass
очень хорошо
are
проверяют
important,
и
that is, and
стараются
it's being checked very
компенсировать
well
действие
before, and we try
невесомости
to
врачи и
compensate, to
исследователи.
counteract any negative
Во время
condition
длительных
by the
полетов
doctors. But
значительно
during long-term
меняются
flights,
кожные покровы.
there are significant
И
changes to the skin
необходимо
surface, and
помнить
that is
в
important
этой ситуации
to
как раз
remember
о
under these
матриксе,
conditions about
о
the matrix,
внеклеточном матриксе, который
about the
является
extra cell
основой и
matrix, which
занимает
is the
достаточно
foundation
большой объем,
of
как
that,
в
and that
коже,
takes
так
a
в
large
мышцах,
amount,
в
that is
суставах,
muscles,
в связках,
joints,
кости
connective tissue,
и
bones,
вообще во
and
всех органах
everything
и тканях.
in all the
Это
organs and
основа,
tissues
на
of the body.
которой
That is the
ну,
foundation
как держится, как в доме,
that is
клетки наших
keeping
органов.
the body alive
И
like a foundation
изменение
in a house.
матрикса во время
And changes of
космического
the
полета,
matrix
мне
during a
кажется,
space
очень
flight
важно.
and studying
Мы
those
не
effects
делаем
are very
открытия,
important. These are not something
говоря о
breakthrough
матриксе. На самом деле очень многие врачи и
developments.
исследователи
In
обращали на
reality,
него
a lot of
внимание,
doctors and
но есть
researchers
несколько трудностей.
focused on that. There are
Это
certain
может быть и не
challenges
вопрос, и
with
не
that.
проблема, а то,
Maybe
что
that's
наши
not a
американские
question and
коллеги
maybe not an
называют
issue,
challenges.
but our US colleagues call it a
Матрикс
challenge.
очень много
So
компонентный.
there are many
И
components
когда
within a
одни
matrix.
исследователи изучают
And when
коллагены и
one
говорят
researchers are
об
looking at
укреплении,
collagen
другие
and they talk
изучают
about changes,
фибронектины и говорят
others
о
look at
изменении этих
fibronucleins and say
составных частей
these
матриксы. Кто-то
matrix
изучает
are undergoing
растворимые
changes. Some other
активные
people are looking
вещества в
at
матриксе.
soluble, active
Это немножко
things in the
распыляет
matrix. So that
знания
kind of
об
disperses
изменении
our attention
матрикса или,
and
как
that
теперь говорят,
disperses our knowledge
Metrosome.
about the
Но это
matrix.
крайне важно,
But
когда
it's
мы
extremely
начинаем
important
задумываться о
for us to think
процессах
about it when
регенерации
we start
тканей.
thinking
И
about the
это
tissue regeneration.
мой третий
So that is
вопрос
my
или третье
third subject,
замечание. Мне
third
кажется,
note
мы
that I
должны
wanted to look
чуть
at.
больше
I
уделять
believe that
внимание.
we should pay a
Мы
bit
это
more
и исследователи,
attention to that.
и
When I say
врачи,
we,
которые, может
I mean
быть, понимают
researchers as well as
больше
doctors who are involved,
исследователей,
because
и
sometimes
глубже
space doctors
исследователь ту
understand a little
опасность,
bit wider and
которая
deeper
в
these
длительных
issues,
полетах
especially
стоят
the impact of
изменения
long-duration flight
регенерации
and
тканей.
how their changes
Они
occur
происходят.
and the issues
Они
related to
происходят потому,
regeneration
что
of
матрикс
tissue.
теряет воду.
They happen because the matrix loses
Не
water.
только мозг, не только
Not only the brain,
объем крови
not only
уменьшается,
the
матрикс тоже
volume of
теряет
blood
воду.
is diminishing, but also the matrix. The matrix loses elasticity and water and loses active components that are connected with the proteins of the matrix. Therefore, I think the regeneration issue of tissues is very important, and we have to pay more attention to that. I think these issues, I'm just raising them right now. Maybe I cannot provide any answers, but I can say that recently we wrote a review, and if you are interested in the results of the review that we have written, I'll be happy to send you a link in the chat to the review that we have published. What we have tried to analyze different aspects of changing of the matrix during space flights, as well as the ground model experiments that we have conducted. The two questions, despite that we have tried to have a very comprehensive review, the two questions still remain. What are they? First, a human, a mouse, a rat, a cell, they are traveling to space with a matrix that was created on the ground. Then the changes in the matrix occur if it's a long duration flight, more than 6 months. And so we have a newly developed matrix because a lot of molecules will be formed, and the structure of the matrix will be formed in the microgravity condition, in the conditions of the space flight. Therefore, when the human, or after bion, a mouse comes back to the ground, then they come back, quote unquote, with a space matrix. But the organism of the body of the animal should now live in the conditions of the ground gravitation. And maybe that is why the readaptation of some of the structures after long-term flights is challenging, and it takes a long time. Sometimes restoration of the water content is pretty fast after the flight. Mike, I think with that, I'd like to stop at this moment, and should there be any questions about or discussions about bion, then I'll be happy to jump in and comment. I don't want to bring everything in the same basket of issues, as it were. These are the three questions that I have voiced. Anything else I can talk about later, but our lab is focusing on those three issues right now, bio and M2.
Okay, thank you so much.
Thank you.
I think this paper that Ludmila mentions, it's a lovely review. It's the microgravity effects on the Metrosome. And here we go. It is published in the journal Cells just a few months ago, microgravity effects on the Metrosome. And it does elaborate on a lot of what Dr. Buravkova mentioned. And we certainly don't expect these panels to make everybody here an expert. We really do expect to pique the interest and the curiosity, and to give the context of why these new findings, I think, are extremely exciting. And I think people can easily understand we can't grasp the complete and holistic response of the human to spaceflight without understanding the cellular level. And I think that's very nicely explained in this paper. I'll just make one comment, and I think Dr. Buravkova and I share this a bit of anxiety and hope, which is the possibility of applying some of the new genetic methods. And we were talking about genetic polymorphism in particular. We believe that that's very important, but there are a lot of concerns because we've never had the tools to give us this depth of knowledge. And there's a bit of fear about that. And it's something we need to learn to apply carefully and without fear, but really to understand the human response. And I would say that applies to almost any novel environment where the human has to adapt. We have some studies going on, certainly Dr. Scott Smith's studies with the one carbon chain polymorphism have given us a very strong glimpse into a biochemical mechanism that correlates with SANS. You really do have to identify and follow these leads very carefully. So hopefully we will have some questions on this when we open the floor to everybody. But thank you so much, Dr. Brooke Kova.
Thank you, Mike.
Thank you. We're going to switch gears a little bit now and move towards the analog environment, if you will. Now, we're very lucky again to have Loredana Bessone. Actually, almost everybody on this panel was time challenged to a certain extent. Dr. Bessone holds master's degrees in computer science and space systems, and she's been with the European Space Agency since 1990. About the same time I came to NASA, so we're similar veterans in time, although I think she's come through it much better than I. She supported the EuroMir program in the mid-90s. That's when I first bumped into her, working with our Russian colleagues in the Mir program. And in that time, she was developing and training and managing all aspects of instructional technologies and training for Issa astronauts, as well as the ground support folks. Since 2004, Loredana has been pretty much at the forefront of building expeditionary behaviors, if you will, in Issa and international astronauts as well. She led the development of outdoor and survival training, as well as human behavior and performance training. And she's actually trained the winter over crews of the French-Italian Concordia station located at high altitude in Antarctica, mostly focusing on team dynamics in isolated and confined environments. Loredana has designed, developed, and directed the Issa Caves program. This is a spaceflight analog for human behavior and performance, which I was very fortunate to take part in. This applies to astronauts from all ISS partner agencies, which I can say from experience is a spectacular but demanding and highly effective training analog. In recent years, she's developed a field planetary geology course called PANGEA. It is an acronym in true spaceflight fashion for Planetary Analog Geology and Astrobiology Exercise for Astronauts. Well done, Issa. And a field test campaign on planetary analog environments more recently. This is called PANGEA X. So very mindful of our current focus towards renewed surface activities, the Moon and Mars. And along with this is the development of an electronic field book, which will be tested at these venues and ruggedized for use on the lunar surface. I've asked Loredana to talk a little bit about this new program, and I will have to say that she's just wrapping up a field exercise, and I honestly don't know where she is right now, but we're very lucky to get her. So Loredana, I'll give the floor to you.
Thank you, Mike, and thank you to the Baker Institute. Can you hear me? Okay, and thank you to Baker Institute and to Rice University for inviting me here. I'm still baffled that you invite me to this panel. I'm finding my brain definitely is lacking a lot of the ability that everybody else has around here. I'm not a scientist. I work with scientists. I love working with scientists. And what we are in here in Lanzarote in Spain, in a volcanic environment that really looks like Moon and Mars. It's an analog, yeah. It's an analog where we take astronauts to train them as field geologists. You mentioned caves, you mentioned analogs. My use of analog is very varied, in fact. I think analogs are really a fantastic environment to take astronauts in places where they are not familiar with and where they have to really get into the mood of learning the environment, understanding and observing, and getting to not to control it, but to be controlled by the environment. And that actually changes the way they think through exploration. But for us, PANGEA actually was coming out of caves in a sense, because during caves, and when you were there, Mike, you were a scientist, you are a scientist. And when we asked you to look for signature of life and to collect samples of microbiology, you knew what to look for, because it's never easy to train somebody to look for something, to observe, to find something which is relevant for scientists if they're not scientists. And the being a field scientist is a very, very different skill and education than actually being an astronaut overall, because as an astronaut, most of the time, you're still working in a lab in an International Space Station. And in the future, planetary exploration will take astronauts to planets, to real environment, and to the field. So yes, they will need to be engineer. Yes, they will need to do maintenance, but pretty much they will need to be on their own as field scientists do. And this was a shift. Suddenly we started thinking like, okay, we don't need to train astronauts. We need to educate them. We need to transform them in something that is allowing them to communicate with scientists using the same language, and will require also the scientists to actually change their language in order to be able to operationally understand each other. The collaboration needs to be different. So if you want an astronaut to be the eyes and arms and hands of a scientist and be able to communicate, you need to change the mental models of both and make sure that they actually talk about the same when they are discussing. We usually train astronauts for tasks, but now we need to change the in a Bloom taxonomy, you need to higher the level that you go to. You usually train astronauts to comprehend and apply, to follow a procedure, to be aided still in performing complex tasks. Now we are talking about getting astronauts to exercise the ability to analyze an environment, to make decisions on their own, to form hypotheses together with the scientists, and to have an autonomy level that is totally different, to be able to take decisions at a different level of autonomy, executing in an autonomous way, and be effective in operation and efficient in the interaction. So in a nutshell, they need to be scientific explorers and be able to document and be willing to document, because they need to understand what to document. So it's a totally different level to me of involvement, of understanding, of valuing what they're doing, to be able to really read the environment and go in. And with that, you need to find the right analog environment, obviously, that are representative enough, and no analog environment is representative enough ever. So you need a various level of analogs. Each one of them will have one element that you then put all together to build the big picture. The big picture will never be total until you go to a different planet, but each one of those analogs needs to be carefully selected. And I've seen now a lot of popping up of analog activities, but the key sometimes is just, I want to be there in the field and bring people in there. I mean, that's not what you want. You need to have an objective. You need to know what you want. So finding the right analog and finding the right instructors, because as in your case, I mean, you need to be having in front of you real scientific explorer, people that you totally rely on, people that are models for you and you actually believe on. We are used to having instructors that are professional instructors, but actually acquire knowledge and then passing on to astronauts. Now that would not work in this environment. You need to have somebody who's able to really say, okay, I have experience that I acquired for 30, 40 years, and I'm now passing it on to you in a very concentrated way, because still, I don't have years of education to actually bring astronauts to the field. But with mixing with a right mixture and with the right sort of building up of knowledge, I think you can get to the level where you create field explorers. And I can say, like, we had Kate Rubins here from NASA, one of the Artemis team astronauts, and with Andy Mogensen in the last traverse we had just a couple of days ago, they were able to form a hypothesis together about what was the geological processes that happened in the site that they had to traverse by themselves. And at the end of it, at the end of 3 weeks, we had them at higher level of not knowledge, but field abilities than third-year master level on field geology. And this is something that was, I mean, it's a very high achievement. And I think from then on, and we've seen with past students, they are able to actually communicate and start discussing at the same level as geologists. And this is, I think, is what we want to be able to have them being able to really be collaborative. So I think at the end, what we really want is to make sure that we create teams that, as I said before, have the same mental model, have the same language, and have the same value in what they want. Because just yesterday, I was interviewing one of the instructors, and I say, what do you want from the astronauts? Say like, well, I want to make sure that when they get there, they're me, because I can't get there. But now I trust them. They will be me. They will do what I want. I know that if I ask them something, they will understand how much I care for those rocks, and they understand that those rocks are telling a story. So I don't really have a lot more to say about it. I can talk more about the structure of this course, but I don't think this is really relevant. I think mostly what I want is to say, like, analog environment and the way we train astronauts right now needs to be different, because we go from having astronauts that are spending certain time in executing a very, very structured program that has been pre-thought by hours and hours of work of a lot of engineers, to obviously still go to a very structured program, but need to go much more into flexible execution of command, and being able to become autonomous, not just in terms of being a little bit more autonomous, but really being conscious of what they're doing and feel responsibility for what they're doing in a completely different level. But they can't just be trained on that. They need to be educated and be field scientists for that. Well, I'm thanking everybody, and I'm also open to questions, but sincerely, I don't think that I can add much more to that, because I mean, telling you more about the structure of the program, I don't think is important. I think the message for me was what I just said. And if it's not what you wanted, I'm really sorry.
No, that's perfect. And there will be some questions. However, I will have to say, don't sell yourself short for not being a scientist. First of all, you have degrees in computer science. Secondly, I have seen you take scientists and stress them and make them cry and sweat. But in the process of that, you're turning them into field scientists and turning them into explorers. That's a vital function. It's huge in the broad picture of human spaceflight. I do have one question before we move on, is aside from me, what kind of feedback have you gotten with regard to your training from people that have actually gone on to fly long duration flight or be crew members winter over in Concordia?
Well, it's now for Pangea, obviously I got feedback from Chinese, but that's not relevant at the moment. I mean, for Caves, actually I had very, very interesting feedback. Takuya, for example, was there with us last year, and they say, like, I got one comment from my crewmates: I've never been into an EVA, and now I'm told if I want to go to an EVA, I'm ready because I did Caves, which is quite very interesting, very, very interesting topic, because in reality, Caves is not preparing you for an EVA, but actually the mental model that you have, the type of safety issues that you have to address, the type of processes and protocols that you have to use are very, very similar. The kind of comments I got was that usually is not only for the training, but for the type of interaction that there was and the kind of reinforcement of what they were learning from people like you that had already been in spaceflight before. There was an analogy that could immediately be taken. And the step, I think the most of the learning is not in what you learn now, but how you project it to your future, and that projection, I think, the most relevant. And that's why, at least in Caves, that's very different from Pangea, mixing experienced astronauts that have experienced something and new astronauts that have not yet had a chance to experience the new environment. Actually, it's very important. Now, Caves is very different, as I said, from Pangea right now, so I don't know what the feedback will be in the future about having taken Pangea. The feedback we got right now from participants is that they feel ready to go to the next step of training, which definitely will be much more focused to one specific mission or one specific set of operations, which are not ready right now, but they feel like now they're confident in being good field geologists. So that's like what I can say right now. I think you are a much better example to give feedback about the training than me, because you have been there.
Well, I thank you. I would say that you are probably one of the most spaceflight ready people on the planet because of the training that you've developed. I did find caves to be unexpectedly an extremely good analog for EVA, especially surface EVA. But if there's further interest in that, Issa does a terrific job of producing video documentation of their analogs and caves in particular, and those are really quite good. So thank you, Loredana, and you can anticipate a few more questions as we go, so hang on with us. We will continue the theme of analogs here, but we're going to shift from field analogs to a much more high fidelity research mode, which does both prepare those expeditionary behaviors and the technology we need to support people in these venues. So we're really lucky to have Dr. Grace Douglas with us. I believe Grace was on early morning with the onboard crew on the International Space Station this morning and scheduled that early so she could be with us. So we're very happy for her doing that effort for us. Dr. Douglas serves as the lead scientist for NASA's Advanced Food Technology Research effort. Excuse me, and this focuses on determining the methods, the technologies, and the requirements for developing, good, safe, nutritious, palatable food systems that will keep us healthy during our long-duration space mission. Now, most of you who know me well know that I really love to eat. Food is huge. If I don't hold the record for in-flight calorie intake, I'm probably close to it. And food really keeps your crew together. That's on the surface. Underneath that, it has to maintain performance and health. So her very large responsibilities include assessing the risk of an inadequate food system to crew based on the vehicle design, the mission architecture and concept, and really developing the research that will cover those knowledge gaps and ensure the food system meets our health requirements. She has degrees in food science, masters from Pennsylvania State University and North Carolina State University, and did her doctorate work in functional genomics from North Carolina State University. More recently, Dr. Douglas has spearheaded the CHAPIA project, another lovely NASA acronym, but I like this one actually, Crew Health and Performance Exploration Analog. So this will be long duration, very Mars forward habitat analog based around food, nutrition, and crew support. So we've asked Dr. Douglas to come and talk about this project. And again, we're very lucky to have you. So Grace, I turn it over to you.
Thank you, Mike, and thank you for inviting me to speak today. Can you all hear me? All right, great. So as Mike said, I'm going to talk about the Crew Health and Performance Exploration Analog, which we are currently setting up right now at the Johnson Space Center. And this analog will be a set of 3 one-year missions that will begin in 2022, simulating Mars surface missions. And these will have realistic spaceflight resources, realistic food systems, isolation and confinement for the crew for the 1 year, time-delayed communications. So we are going to start instituting some of that realism and that they won't be able to be supported through a lot of the events. We'll have mission-relevant timelines, and then we're also going to introduce contingency situations. So we will throw some challenges at the crews that they're going to have to work through. And the goal of this is to see how those resources, and especially how that food system, is supporting their health and performance through that time. And we have very specific ways we're going to measure that through the mission, with the goal that we can then inform the program of the risk with the resource trades for having certain systems in place. And each of the 3 missions will be close to identical, but with 4 different crew members. So the crew are going to end up being where a lot of our differences might come from between the missions, but that's why we're trying to keep them so close, so that it can be a scientific process, that the health and performance outcomes we get will be repeatable. So the reason that we did want to set this up is that when we look at the ISS, even though it is a restricted food system, all food systems in spaceflight are restricted just by their nature to mostly prepackaged foods, and then, of course, to what is available during the mission. On ISS, they get a lot of resupply. And right now, about 25% of the foods that they're consuming are from some of the fresh foods, the crew preference foods, their choice foods. A lot of these foods will not be available as we go on a Mars mission. And yet crew on ISS are asking for more of these foods. So this becomes a challenge because even on ISS right now, we never designed the food systems specifically to be maintaining crews over long durations or to mitigate disease incidents, because these are prepackaged long shelf life food systems, and we don't really have an understanding of how those influence over time. So despite that we do have general nutritional adequacy, these food systems have always tended to be underconsumed, and we do see about 5% body mass loss, and we can see even higher body mass losses. We've seen up to 10%, and military studies have linked those kinds of body mass losses with cognitive and performance decrements, but we have not been able to evaluate these sorts of decrements in our own crews to date in relation to the food system. So we know we see decrements in spaceflight, but how do they relate to nutritional intake? And that is one of the goals that we're trying to get at here, so that we can start to say we really need to have food at this level for these missions to support these crews at this performance level if you need it for these missions. And food currently is a mass driver and a red risk for Mars because we do not have a food system ready to support exploration or an understanding of how expected limitations might impact health and performance. But throughout history, food system failure has been a primary cause of exploration failure and human settlement failure. Basically, it's been number one. So even with this risk, that food is a red risk for Mars, current programs for Artemis are cutting food system requirements because food's heavy. It's a high resource user. And so without having the knowledge of, well, how is that going to impact crew performance? How is that going to impact crew health? Even on these short durations, they cut those systems without knowing what's going to happen because it's such a high resource user. So we really need to be able to start informing them on how those weight losses impact performance and cognition even over the short term. And this is going to be a big knowledge gap to fill for the long term to make sure that when these crews are so far away that we cannot send them extra support and we cannot bring them back, we do have systems in place that will support that health and performance. So those are really the big goals. And this becomes important to understand on this timeline because ultimately this food resource driver is going to have to influence the Mars transport vehicle design. Right now, over half of the logistics to Mars are expected to be dedicated to food. And there are a lot of assumptions right now that we can reduce that mass of the food system. So we really need to understand this baseline impacts of what we expect a Mars food system could look like and how we expect that's going to impact crew health and performance. Once we get that baseline, if we do start making cuts, then we can really understand how those cuts are influencing crew health and performance in that risk resource trade. So ultimately, our two main goals are to characterize the risk of the planned food system and its impacts on health and performance. And we're going to be measuring behavioral health, physical health, and also performance factors through EVAs and exercise throughout those missions. And in addition to that, we are building a habitat right now, which is a 3D printed habitat using a new technology. The Icon company is building that habitat for us, and it is using technology that could potentially be used on a planetary surface in future to build a habitat. So and we're trying to bring in a lot of other groups around NASA that could potentially require long-term testing for some aspect that will not influence the primary objectives that we're trying to understand within this study. So we have a lot of other things coming in right now. And so I think at that, I'll probably leave it at that and just wait and see if anybody has questions.
Let me just ask one question really quick. We're building this now. What do you expect the crew size to be? And just to be sure, these are 1-year missions on the dot. Is that what we're looking for?
They are. So we're going to plan for 4 crew. We are going to have a training period prior. So we're expecting to start training in September of next year. And we're expecting to start the mission in October of next year. And the missions will actually be 378 days in order to set up the experimental design to be the most relevant. It is just a little over a year.
All right, so this is not for the faint of heart, for sure. I think some of you probably get the idea that Dr. Douglas's world is justifying feeding crew. And when you hear numbers like half the resources to Mars are going to be food, that's something that, with all due respect, mission planners kind of choke on a little bit. And the last thing they want to see is food left over. We like everything to be as surgical as possible because the cost of getting resources to Mars or really anywhere are so large. And I like to point out that I believe we kind of live in a golden age of food in space right now on the ISS. No matter how much people complain about it, the food is really good. It will never be better in space than what we have on the ISS now. And that goes downhill immediately as we start to head for Mars when you're thinking about durations and resupply. So that is Dr. Douglas's world, and she's kind of a champion of keeping us healthy and that and asking for a lot of resources. So we're behind you all the way, Grace, I'll tell you that. All right, there will be questions on this to come. Let me move on. We're going to change gears just a little bit. We're going to move from analogs now to more systems that are under development to support our new exploration initiatives. Now, I think it's a foregone conclusion that astronauts will be donning a suit and exploring the lunar surface and doing that in earnest. And that's what people expect of our return to the moon and of course, going back to Mars. Some of you may know that our current fleet of EVA suits, which have been wildly successful, I have to say, that we've been using them throughout the shuttle program and the ISS, but they are now older than some of the astronauts that are using them. Which I think is quite remarkable. It partly reflects we've started selecting people a slightly younger age, but don't think that's a big part of this equation. These suits have been operational and serviced and maintained and highly successful for a long time. But we do worry about that. So here to talk about, I think, a really exciting project, and I would say a very critical one, our next generation suit is Mr. Kevin Wells. Mr. Wells is originally from Baton Rouge, Louisiana, and he has a background in biomedical engineering from Mercer University. He began working at NASA in 2005, and he started developing EVA repair tools for the shuttle thermal protection system on orbit repair procedures. This was, of course, in response to the Columbia disaster and knowing that we needed this critical capability to resume flight. So the bar was set very high on developing that capability before we could safely get back to shuttle flight. He spent several years in the EVA office managing the extravehicular mobility unit, the EMU, for both the shuttle and the ISS, and then he served as the chief engineer for the EVA program. Kevin now serves as the chief of the Spacesuits and Crew Systems branch in the engineering directorate, and he's here to give us a few words on our next generation EVA suit. So over to you, Kevin.
Thanks, Mike. Can you hear me?
Got you loud and clear.
Okay, great. Thank you. All right. Good morning, good afternoon, or evening as it may be to all of you. I wanted to thank Mike for inviting me to come and talk about our spacesuit development, and also to the Rice University and the Baker Institute for hosting this forum. So I wanted to basically go through a few details of the development that we have underway in producing the next generation of spacesuits for NASA's exploration missions. And these spacesuits that I'm going to talk about today are the EVA kind, right? We also do launch and entry suits within our branch. We're going to focus on the EVA suits in this discussion. Most of you have seen images, I would assume, of the Apollo suits. That was 50 years ago, over 50 years ago. That suit was, of course, first deployed on the lunar surface. And then, as Mike mentioned, we've been using the EMU, which stands for Extravehicular Mobility Unit, another great NASA acronym, for the last 40 years to support the shuttle and the station programs. Those two suits are very different. And as we looked forward at what NASA needs to do exploration missions, we need both planetary surface suits like the Apollo suit and microgravity capable suits like the EMU. And so we have attempted in the development of what we call the exploration EMU to capture the best of both of those sides of need, or best of both of those areas of missions. So just to give you a sense of the kind of design drivers that have been guiding us in the development of the XEMU, we do want to be able to support those multiple missions in those different environments, so planetary surfaces, deep space, the lunar gateway, all of those different environments. And we want to be able to support longer duration missions with minimal servicing, and we want the hardware to be able to endure for longer quiescent periods. With the current EMU, we are relying on regular servicing on the ISS. It's fairly intensive in terms of crew time and resources. So we want to improve that picture to support longer duration missions with less regular maintenance or servicing, and especially less regular rotation of hardware from the ISS to the ground, which is currently part of the way that we manage the EMU. We also need to reduce the consumables and the need for replenishing consumables in our suits in order to reduce overall system mass. The current way we remove CO2 from the suit is extremely heavy when you look at an exploration mission mass profile. It's far too heavy to be supportable for a long duration exploration mission. We want less crew time involved in actually maintaining the hardware and preparing for an EVA. So what we call on the ISS the road to EVA, between the decision to go EVA and actually getting out the door, we have to minimize that timeline and the amount of crew time that's involved in getting there. And then we want, of course, to have a modular architecture with standard interfaces that allow us to move between different vehicles, different habitats, potentially even across different suit systems, in order to make the hardware and then to be able to resize, to repair. We need that modular kind of architecture with standardized interfaces to make that possible. We also need the hardware, of course, to be very reliable and rugged in the face of some very challenging environments on the lunar surface and the Martian surface and beyond. And we need component technologies that do their job across that range of environments, from the vacuum of the lunar environment to the Mars atmosphere. And then we need to be able to enable the astronauts wearing this portable life support system and anthropometric pressure garment to be able to work as closely as possible to the way a geologist would work here on Earth. That's going to improve their science ability, their ability to gather science and to get results for the investigators on the ground. It's going to enable them to become those scientists that we were talking about earlier with the way we train astronauts. And then we need to reduce the possibility of injury for crew members during EVAs. EVA is by nature a very rigorous activity, and we have seen crew injuries over the years because of the way the suit and the environment and the human work together. So we want to reduce the possibility of those injuries. And then finally, we want to improve the range of humans which the suit fits. We have been working on that for many years. There have been budget constraints in the past that honestly limited our ability to fit. But we want to do that with fewer different sizes in the suit, because that was one of the budgetary limitations that led to a limited range of fit for the EMU. So the fewer size components that we need, but the wider range of fit that those size components will accommodate is really the goal. To maintain lower cost, but also improve the fit. So when I talk about an EVA spacesuit, we really think of it in three different major subsystems. The first is the pressure garment subsystem. So that's the thing you see, right? The white suit that is its main job is to provide for mobility of the human in the suit, to keep pressure, to maintain a habitable atmosphere within the suit for the crew member. Then we have the portable life support system, right, which many people think of the backpack. That is where you are getting your oxygen from, which provides both for oxygen for both breathing and for pressurization. It has to remove trace contaminants and the products of human metabolism. We have to be able to maintain thermal control, as well as primarily remove CO2. That's our big thing that we've got to get rid of in the suit. And then we have to provide cooling for the crew member. In that system, we also have to provide, and this is where Jason, who's going to be speaking in a little bit, and I spend a lot of time talking about the provision of hydration and nutrition for crew members. That's something that we have had limited capability on with our previous suit systems. But our physiologists and our medical doctors are driving us in the hardware world to make sure we accommodate better in-suit nutrition and better in-suit hydration capability. And then the third major subsystem is what we call informatics. This is kind of a newer system. We hadn't really broken it out that way in previous suit systems, but with the improvement in electronics and communication and the amount of data that you can deliver from a spacesuit back to a vehicle and onto ground controllers, as well as the amount of data that you can provide to a crew member to improve their operations in the mission and in the environment, that's going to be a key part of the future of spacesuits. So I want to turn for just a few minutes to talk about some of the advancements that this current suit system under development is featuring over previous suit systems. So we'll start with the pressure garment subsystem. Obviously, and for this audience, I think probably a key thing of interest is when you get into a spacesuit and you work in that spacesuit, and our EVAs, we think will probably be on the range of 4 to 8 hours. But when you look at the total time of pre-breathe and preparation for the EVA, all those kind of things, you may be in the suit for as many as 12 hours at a time. The suits, you are fighting against the pressure in the suit during your entire time in it. So we are working on the pressure garment system to try to make it as mobile as possible, to reduce joint torques, to reduce the effort the crew member has to undertake to actually move the suit and work in the suit. One of the things we've done with the current design is we've moved from a waist entry to a rear entry for donning and doffing. That is something that we think is going to be helpful in reducing the possibility of crew shoulder injuries that have been an issue with the current EMU design. It also it creates some challenges in terms of space within a vehicle, but we think it's the right trade going forward. We've worked significantly on the mobility of the spacesuit at the waist and at the hips. That is, pardon me, the waist, the hips, and then the shoulders. Trying to reduce the joint torques in those areas is really key to making the suit work like the human works, and making the suit as transparent as possible to the human when they're working in it. And of course, being able to have a mobile lower torso is essential for doing a planetary EVA. The Apollo suit was actually a soft suit. It did not have any bearings or metal components that provided that kind of structure and provided mobility in that way. And so while there were some benefits to that, it certainly was a lot more difficult, required a lot more effort to move your elbows, your shoulders, your knees, your hips in that suit. And so we're improving that with some metal bearings in certain places. We've also changed the helmet shape and changed kind of the dimensions and the way that we're positioning the head within the helmet. That's for increased visibility. As you're walking on the surface, you need to be able to see your feet. For safety and for navigation. And so we've changed the way that the shape of the neck ring and the helmet bubble interface with the face of the human to make that possible. Another significant change that we made is we're getting away from what has traditionally been called the Snoopy Cap, which is your communications cap, which holds your microphones and your speakers for your ears. There's a lot of benefits if you can get away from a cap and instead have an integrated communication system within the pressure garment. That's also a big challenge. You're having to deal with potentially multiple pressures, 4.3 or 8.4 psi, so very low pressures. So your sound pressure is a challenge. You also have to eliminate feedback and noise from the sound of the ventilation loop and airflow within that helmet area. So it's been a challenge, but we're using advanced algorithms to make that work so that the crew member has a more natural feel in the suit in communicating and in being able to move their head and experience cooling, those kinds of things. Another huge challenge for the pressure garment subsystem is is protecting the suit and the crew member and the vehicles and habitats from the introduction of dust from the lunar regolith or Mars regolith. The dust can be very destructive to hardware. It's certainly not something we want the crew members to breathe. So figuring out ways to have the environmental protection garment, the outer layer of the suit, provide protection is a key focus of the design. So let's talk a little bit about life support subsystems and the ways in which we are improving the life support system. One of the big things we've done with the XEMU is add a secondary heat rejection system for contingency scenarios. If you're on a lunar surface trying to get back to your vehicle or your habitat and you lose your primary thermal control system, your level of exertion is such that you can quickly get overheated. So we think it's prudent to have a secondary heat rejection system that can provide contingency cooling to the crew member. We are working on a different way of removing CO2 from the suit as well. The current system that's in use in the EMU is very heavy, which works fine on the ISS, but is not something you want either in the mass of the removal cartridge in the suit, just from on the backpack weight, but it's also just consumables heavy. It requires an oven to regenerate. You have to have multiple cartridges that are very heavy. So we're moving instead to a rapid cycle amine swing bed system. It's similar to a system that's been pioneered on ISS, but uses that amine to remove CO2 and water and dump it overboard. And the swing bed allows you to absorb on one bed and dump on the other, and regenerate that bed real time. We're also moving to a new system of heat rejection, so using a single water membrane evaporator instead of a sublimator. The traditional heat rejection capability was basically putting a water to a fine mesh screen and allowing it to sublimate away and cool off a chunk of metal to serve as a heat sink, and then running your cooling fluids through that as a heat exchanger. So we're moving to this membrane-based system, which is, we believe, going to be much more resistant to contamination fouling, which has been a problem with the existing sublimators. We are completely rethinking our control system for the suit. The suits need to be a combination of really advanced and capable in terms of controlling the life support system to meet the needs of the human, but also be very simple in the control scheme, because you really can't afford for it to fail when you're out there doing an EVA. So we're working on a simple but capable control scheme, distributing controllers throughout the architecture so that you can minimize the effect of a single controller failure, as well as have ways of getting out of that and handling that contingency. Obviously, we're working to minimize the battery capacity needed and the power consumption, and still have robust battery capability within the suit. So those are some of the key areas there that we have been working to develop improvements in the capability of the suit system. We're also working in the avionics area and informatics area to improve lighting and for tasks, especially on planetary surfaces. When we think of the lunar South Pole, for instance, the lighting conditions are extremely challenging. So you need very good lights, but you have to also balance your power requirements for that. And then outfit the suit with better cameras than we've ever had in the past. We've been working that and developing that slowly with the EMU on ISS, but we of course want to see, as the astronaut sees from the ground, as much as possible. that helps our principal investigators on the science side. It helps vehicle operators who are based in the vehicle while others are EVA. So that kind of awareness is going to be key. So those are just a few of the ways that we're trying to develop the system and improve it. And so I think I'll wrap it up there, Mike.
All right, thank you very much. I will make one point is that, EVA is probably going to be always the most physically demanding, and once we're on the surface, the most dangerous thing that we do. And we're basically asking these guys to do the impossible, right? So they have to build a miniature spaceship, an EVA wardrobe that fits almost everybody, along with a set of tools and something you may have to be comfortable in for up to 12 hours. But also bear in mind that our new lunar exploration initiatives are a little bit different from the Apollo era. We're going to more interesting places with much more challenging terrain, much more challenging landscape. We're going to be asking these guys to do a lot more physical activity and sampling and exploring and potentially construction and more EVAs per suit than we ever did with Apollo. So we're taking many quantum leaps here in capability. So it's a really big deal. Kevin, I'll just ask you quickly before we go to Jason, knowing that there's bids in play, is there a place that people can go to find out a little bit more from NASA about all these factors that are being improved right now and developed?
Yeah, that's a really good question, Mike. Of course, there are sensitivities with procurements as NASA tries to make sure that those are handled fairly. But you can go to sam.gov, and that is where you can find actually the request for proposals, which has a ton of information about what NASA is looking for and asking for. And that's probably the best place to do that in terms of the most data. You can also go to nasa.gov/suitup, SUITUP, and there's a wealth of information there. Some of it may be a little bit, maybe several months out of date, but it is actually got a lot of good information there about the kind of work we're doing and what we're asking for from our contractor partners going forward.
Okay, superb. All right, thank you very much. We're going to wrap up with Jason Norcross, who's been very patient there, but he's pretty much always that way for those of you that know him. We're going to talk a little bit more about the human interfaces, the biodynamics of the suit and habitat atmospheres, how that dovetails with suit operation. I think it's safe to say that along with really good food, we'll probably leave sea level pressures in low Earth orbit as we venture outward. There's good reasons to do that, but it really changes the dynamic. We have to basically build and tune an atmosphere, and that has to dovetail with the suit pressure as we decompress to suit EVA pressures. Really quickly, Jason Norcross, known to many in the community as senior environmental physiologist within the NASA Human Physiology Performance Protection and Operations Laboratory, otherwise known as H3PO, or we just say the Hippo Lab. But I'll say that this group has been extremely busy recently developing atmospheres, decompression schedules, and informing other aspects of biodynamics, as what I would say record numbers of new spacecraft and new mission scenarios are being designed. Jason's area of research and interest include human performance in spacesuits, decompression sickness, closed loop life support, and human systems integration. And I did ask Jason and one of his colleagues, Simo, to see if one of them was available. The other one is actually sitting in a chamber even as we speak. And so these guys don't spend a lot of time on paper. They really build, they do, and they produce. I've asked Jason to give a few words about the suit interfaces and exploration atmospheres and balancing habitat and EVA operations. So over to you, Jason.
All right. Thanks, Mike. Are you able to hear me okay?
Got you loud and clear.
All right. Wonderful. It's hard not to just jump on and ask a bunch of questions and provide feedback on Grace, Kevin's talks. These are folks I work with pretty regularly. But I'm going to stay on script and walk you through kind of where we're going in this direction. So as we've been talking, ISS, it's a science lab. EVA is not the prime way that we conduct our science. It's kind of what's used to maintain and make repairs on the International Space Station. So EVAs are relatively infrequent we use a sea level atmosphere so that we don't have kind of an odd atmosphere as another confounding variable when we talk about life science studies that look at using ground controls, and then you take away gravity and you want to see what's happening. So when we go through an EVA, it is very much it's sort of like an aftermarket add-on to a certain extent. It was not fully integrated with this approach. So we start, the crew members arrive on the day of EVA. This is before you've done the EVA planning and things like this. But these are all the things you have to walk through before you actually go out the door. You start with a mask pre-brief because people don't want to just suit up and do everything in the suit. So you start with the mask pre-brief, and then at some point in time we have to take that mask off, and that's going to be a break in pre-brief. So we partially depressurize the airlock on the International Space Station to about 10.2 psi. And then you don the suits, their waist entry. Kevin didn't spend a lot of time talking about kind of the waist entry versus the rear entry part, but the way these suits are donned, they require kind of a buddy to do this. So you're going to have at least one more person, at least 3 people in there to suit up the 2 people going out for an EVA. Once they're suited up, they've completed the nitrogen purge and they're breathing oxygen in the suit, then you repressurize the airlock because you got to send that other IVA crew member out. And that's fairly consumable heavy. You're using a lot of oxygen. The good news is that oxygen gets pumped back at the station and the rest of the astronauts get to breathe it. It doesn't have to go overboard or something else. So it's a reasonable trade. Once you have then repressurize the airlock, you complete the rest of your in-suit pre-breathe. We use a little bit of exercise to enhance that pre-breathe. And then finally, you close the hatches, depressurize the second stage of that airlock, the crew lock, and the crew begins their EVAs, roughly 6 hours after they started this whole process in the morning. So when you're doing that just once in a while, it's okay. But when EVA, as we move into these exploration missions, like on the moon and Mars, when we go there, is the way that you do your science. We need to figure out a better way to transition from inside the vehicle to outside the vehicle. So, hence, the most obvious change is to use a different atmosphere. And we have been talking about this for as long as I've been at NASA and before, and it's always a trade. We're going to use an atmosphere we call the exploration atmosphere. It runs at 8.2 psi. And then as we reduce that pressure, obviously we would reduce the partial pressure of oxygen. That's not good. It's about 18,000 feet for an altitude comparison of where that 8.2 psi sits. So we enrich the oxygen from 21% to 34%. We'd like to go higher, maintain a normoxic atmosphere, but at some point in time, you run into problems with flammability. So again, all of these are trades between the engineering capabilities and the human performance aspects. So ultimately, we're going to live in an atmosphere that's roughly 4,000 feet equivalent air altitude. We believe that's a mild hypoxia that will be well tolerated, but it is an additional stress that goes on top of all the rest of the stress with space. So we just can't ignore it, but we do have to pay attention to that. We believe that this atmosphere is really going to facilitate a very quick transition between being inside the vehicles and being outside the vehicles. And that's why, as Mike mentioned, some of my colleagues, Andrew Abercrombie or Alex Garbino, both who could have just as easily given this talk, they're in the chamber right now preparing for a saturation 11-day study where we're going to have 8 people locked in that chamber doing an EVA simulation every other day to look at the decompression stress associated with EVAs done at typical suit pressure of 4.3 psi from this 8.2 psi, 34% oxygen atmosphere. And we believe that by reducing that delta P, really it cuts the nitrogen partial pressure in the tissues in more than half. And we're going to be able to use, rather than hours of pre-breathe, more like minutes, something on the order of 15 to 30 minutes along those lines. And by doing that, you can then eliminate the mask pre-breathe portion. and make it much more simple that you suit up, you put on your clothes, you put on your liquid cooling garment, you get in the suit, close the hatch, purge the nitrogen out of the suit that you brought in when you got in, and then complete a short pre-breathe. Now, what's unique about that too is that the suit, as Kevin talked about, and I need to go into a lot of details on this, it's a variable pressure suit. And it can actually reach the same habitat pressure of 8.2 psi. And what's neat about that is that opens up the opportunity for non-traditional airlocks. So something like a suit port, where the suit becomes part of the structure of the vehicle. We looked at these with the rover. It kind of hangs onto the back of the vehicle, and literally you climb in, close the hatch, and you can go and get ready to be out the door. And it just requires much less consumables to pressurize or depressurize something like a suit port, or even something smaller like think about just kind of a very closet-sized suit lock if we have to have some sort of additional support of the suit port alone won't work quite as well. So thinking about additionally these factors, we obviously want to reduce pre-breathe time, but we don't want to increase decompression sickness risk. And when we're out on the moon's surface and we've got higher metabolic rates, greater joint forces, that increases the decompression sickness risk quite notably over what our microgravity experience has been, which has been to date no DCS, but also at the cost of a lot of crew time and a lot of consumables spent on the front end to get out the door. So some other factors is by the fact that the suit can operate at 8.2 psi, we can actually start the EVA at a higher pressure and do what we call a walking pre-breathe, where you actually, rather than waiting in an airlock for you to completely run out the time clock, you can start your EVA. You have no tissue supersaturation, and then eventually you can drop the pressure from 8.2 or 6.2 to 4.3. And we're not talking about hours at these higher pressures. We're talking about minutes, and then you can slowly breathe down the suit. So our options for how we deal with decompression stress and reducing that is dramatically different from what we've had at this point, where the suit only operates at one pressure. We've really got to do it all on the front end. We've got new capabilities where we can start EVAs at higher pressures. And then on the other side, right, decompression sickness is one of these, it's a known thing. We've had to mitigate this from the very first flight that we've taken. So this is not something new. It's something we've managed really well. But we're trying to now manage it really with integrated engineering controls rather than, like I said, kind of aftermarket operational procedures. So the new twist on this is that if a crew member was to get decompression sickness on the ISS right now, you would move in the direction of an EVA terminate. You're going to be within 30 minutes of your vehicle airlock, and that crew heads in and begins the process of repressurization. And that repressurization is really the initial stage of that treatment. But they cannot start that until both crew, and unless there was an emergency case, one crew could go in early, are cleaned up, done, and moved into that airlock. Now moving into the exploration scenario, we have a variable pressure suit. If someone has symptoms of decompression sickness, we can immediately repressurize the suit to 8.2 psi in the field. That is not going to be enough pressure to be a complete treatment. But what it is, I consider this as almost kind of like a first aid. You stop the bubble growth. And by stopping the bubble growth, that lets you say, if you need to take more time to terminate your EVA, clean up, pick up things, you're not under the under the clock now to get back into that airlock for repressurization, because you've already started the treatment. Then you can move to the back of the vehicle and do your definitive treatment. That's also what's helped us to look and say, when vehicles are going to operate at 8.2 psi on the ground, if you can start that treatment immediately during the EVA and bring them back to the vehicle, that vehicle doesn't need to provide significantly more pressure than what it's nominally expected to do. That 8.2 psi from the vehicle plus 8.2 psi from the suit, given a couple different modeling techniques, will be sufficient to address the decompression stress needs. And then the final twist to kind of marry in with some of what Kevin said is, we know that being in a suit for long periods of time is pretty difficult on the human body. And what is unique about using this strategy of exploration atmosphere, potentially suit port, variable pressure suit, is for the first time the overhead to do an EVA is not as high as it's historically been. You know, we're not talking about 5 to 6 hours of EVA prep. We're talking about, you know, maybe from the beginning, a couple hours for the first one. But once you're already suited up, it's a matter of just how long does it take to climb in, close a hatch, and do a purge. So doing shorter EVAs or more frequent EVAs or multiple EVAs, we've looked at the decompression stress with multiple EVAs in the same day, now becomes a possibility. Whether it's the best option is still to be determined, but it is a possibility. And the likelihood of, having problems in the suit, those human-suit interactions, if you're doing shorter EVAs rather than these long 6 to 8 hour ones, it reduces. Less time in the suit means less chance of injury and other problems. So we believe there may be sort of side benefits to this capability, so that now once you go out for an EVA, you do only what you need to do. We're not going to try to maximize necessarily every minute because it costs so much in terms of time and consumables to get out the door, which is how we handle it on ISS now. So whether we use all of those capabilities is still to be determined, but we're going to start learning about it on the lunar surface. So I think I could stop there, Mike.
Okay, I sure appreciate it, Jason. I think it's probably not difficult to understand why the EVA system really is in the critical path of our exploration scenarios and everything we're developing here. So again, we're asking an awful lot of the system, and we really do need a revolutionary step forward, and it looks like that's in work. We have just about 10 minutes left. I would like to open for questions, but I know that we may not get through everybody, so I just want to point out we are posting the references to some of the articles we mentioned, and we'll try to make available some of the websites that might give you a little bit more information about what our speakers have covered. And as we go into questions, I just want everybody to understand that even though we've been to a lot of different places, diverse topics here, all these factors are working simultaneously during a space mission. So that includes the EVA, the stresses on the body, the cellular mechanisms, the readiness for expeditionary activity, the neurobehavioral effects of spaceflight. All of this is a gamish, a fizzing soup of conditions which really define the human performance in this environment. So I really appreciate being able to hear about all these topics. Jason or whomever is online, we will go ahead and open up for questions, and I'm assuming we can just hear voices of people. And if we need to get that rolled, we can start asking some of our own questions as well. Now I'll start by one question. How much will the surface XEMU weigh for, let's say, the 60th percentile male?
Yeah, that's a very good question, Mike. So I think there's still some definitely some uncertainty there. We are working on a suit mass that's going to and trying to keep the system mass under 250 pounds, which sounds like a whole lot. But on the shoulder weight, we're still working on exactly what that's going to look like. When you take the kind of the integrated suit, it's closer to 150 pounds. But we have not yet entered into a serious phase of mass reduction. So we've been working on getting the technologies working and making sure that, we understood some of the trades we had and some of the design developments we've done. And so I think it's still forward work to do significant mass reduction. One of the things that we have to balance, right, especially for planetary surface operations, is toughness and strength versus weight of the materials we use. So we are beginning to examine 3D printed materials and some composites in some key areas, and looking at ways to get really good toughness and fracture and penetration resistance out of those. If you fall down in a suit on the planetary surface, you really do not want to puncture it. So you need good toughness, but you also do want to shave as much weight as you can. So that's still very much an effort that is that's underway.
So
okay, I appreciate that. Go ahead, Jason.
Just to add to that, I think there's a challenge of going back to the moon. I think weight is pretty forgiving. 1.6 G. It's hard to control, but you're not supporting all of that. And the hard thing that I don't think Kevin quite touched on is it's where you have a lot of that mass in your consumables and your backpack and your bearings that allow for this high mobility. If you start cutting mass from some of those places, you're now cutting duration or mobility, as well as the security and robustness. So it is a very challenging trade to figure out, and it's one that I think we can use the moon to learn from. I think it will be forgiving to higher masses, but Mars will not. We will pay the penalty in that free H gravity for a suit, a system that could weigh anywhere from, where it's been multiple 100 pounds. It's going to be a challenge.
Okay, go ahead.
So I was just going to add on to what Jason said. You have an additional challenge in the Mars environment because you're using several technologies that are based on vacuum at the lunar surface, and when you go to Mars, the suitability of that technology is still in question. So we still have to go figure out whether the atmospheric pressure there is going to be enough, and so that actually just increases that mass challenge for some of those key life support systems.
Okay, I sure appreciate that. I'm going to go to a question we had online for Dr. Douglas, which, Grace, you may be able to see that now, but for those that can't, does the 50% of logistics involving food take into account the potential of in situ resource utilization or hydroponics to reduce mass and boost nutrients with nutrients grown on site, such as the recently grown space peppers? How much can we bank on?
There is quite a bit of research that's gearing up in those areas. But right now, there's a lot of logistics to bring that stuff along too. And you have to bring all of that and then start growing something in it. So there will be either a break-even point eventually, or that's also something that goes into your resource risk trade, because having things like a fresh produce when we're not going to be able to have resupply from Earth could become important to human health and performance. But that stuff is not necessarily going to reduce resources, and in fact could increase them, especially for near-term missions or shorter missions. So that's one of the things that they're currently looking at. The logistics include bringing plant chambers, bringing the lights, bringing the nutrient solutions. They say seeds don't weigh a lot, and that may be true, but then what is going to happen to seeds in a high radiation environment? What is going to happen to crops growing in that environment? And then there's a microbiome around that too, and a food safety aspect. We test all of our foods on Earth to make sure that they're safe. We cannot risk foodborne illness in spaceflight, where it would be much worse. We have less medical capability, and yet if we start growing crops or doing any sort of in situ, there's a lot of supplies on Earth that we use to make sure everything's clean, a lot of cleaning solutions, and then a lot of testing, and the logistics of bringing all that with us, or what are we going to do instead to make sure these systems are safe, has not been figured out at this point. So those are definitely things that we're hoping at some point we will be figuring those out as we go along. We will be starting to increase some of those systems so we can figure those out. But right now, they're not necessarily a lower resource solution.
Okay, thank you. I would say from a crew member standpoint, there's quite a leap of faith you would have to take, and you'd really want those systems proven. It makes you feel really good to know that the bulk of food is there waiting for you or being carried with you. So I hate to say it, we have 3 minutes until the next panel starts. I really had several other questions for our neuroplasticity people and for Dr. Buravkova. But we've given you some resources to find out a little bit more about their work. It's ongoing, it's continuing, it's very exciting. So I really encourage you if we piqued your interest in that, go find out more about it. With that, I think we will close this panel. Thank you guys, the speakers, so much. I know a lot of you had to work hard to get here and have very busy, dynamic lives. Thanks for all the people that are listening out there. And again, I really hope we've piqued your curiosity on some of these topics. So with that, we'll close out New Frontiers 2.
Thank you, Mike. Very good panel.